Well, I guess this is take two since the first video didn't work. So, looking on the last couple of videos for my classes, confidence intervals and hypothesis tests for averages. So what we're going to do is we're going to determine how to find a confidence interval for an average, and we're going to determine how to find the hypothesis test for an average. And if this video doesn't work, I'm going to quit for the night. But let's see what happens. So, really, there's nothing too much that's different in this case. It's just that you're using a different standard deviation equation, and technically you're using this thing called t critical value. You don't really. You only use that when it's like less than when the sample size is less than 30. But I digress. We are going to end up pretty much using the same z critical values that we did before. And actually, I won't do this as much in StatCrunch. I would do a couple examples of this in StatCrunch, but not everything will be in StatCrunch. So, let's take a look at this real fast. A poll of 1,000 students was taken, and it was shown that on average, 8 hours. Well, right, that thing has a lot of bad English to it. So it's shown that students study on average for 8 hours when their coursework with a population standard deviation of 1.5 hours. What does a 90% confidence interval for this do? So we're going to go through some similar steps that we did for the other confidence interval. So we're going to start off with first, we know that a 90% confidence interval. This is kind of the thing that I told a lot of my students to remember. Like 90% and 95% were 1.645 and 1.95 respectively. So 90% is 1.645 for the Z star. Again, we don't really use the T thing that I mentioned unless it's less than 30, and we won't really get a lot of those. And honestly, it's negligible at that point anyway, so then what I want to do is I want to use this formula here. And let's see, I have a population standard deviation of 1.5, and then we're going to square root the 1,000. So 1.5 divided by the square root of 1,000. So that gives me 0.0474. Okay, and then what I'm going to do is just like any confidence interval, I'm going to do 8, which is my average, plus or minus 1.645 times 0.0474. Okay, so 1.645 times 0.0474 gives me 0.077. Well, that 9 kind of pushes it up. Wait a minute. 1 second. Just double check my thing. Yeah, that's right. Okay. Yep, we're good. Okay, so 0.0779. So we'll play 0.0780. And then we will do 8 minus 0.078, which gives me 7.922. And then we're going to do 8 plus, which gives me 8.078. And so essentially it's just like before. I am 90% confident that the true proportion, nope, because we're not talking about proportions, rather we're talking about averages. There's no percentages in this one. So the true average of, let's see, of study hours is between 7.922 and 8.078 hours, and that's kind of a big difference there. We're not talking about percentages, we're talking about hours, so just keep that in mind. These are not percentages, these are hours. So we want to make sure that there's an actual unit on that one. Okay, so that's the first confidence interval. Second confidence interval, a survey of 85 randomly selected homeowners finds that they spent a mean of $67 per month on home maintenance, with a standard deviation of $14 per month. Construct and interpret a 99% confidence interval for the mean amount of money spent per month on home maintenance. Okay, so we do have to do little calculations for that 99% because that's not the ones we kind of memorize. So what I want to do for that one is I want to do, for 99%, I'm going to do 1 minus 0.99, and that gives me 0.01. I'm going to divide that by 2, and that gives me 0.005. I want to look at my chart and see which one gives me the closest to that. So, my C-score chart, let's see, 0.005 would be in between these two, so that's in between 2.58 and 2.57, so that's going to give me 2.575. Okay, so then I'm going to get my standard deviation, which comes out to be, let's see, 14 divided by the square root of 85. Because remember, this equates to the population parameter divided by the square root of n. And that gives me 14 divided by the square root of 85, which gives me 1.5185. Okay, so now I want to do, let's see, 67 plus or minus 2.575 times 1.5185. So let's see, if I multiply that together, that gives me 3.9101. And so if I add and subtract it, say it gives me 63.0899, and $70.9101. Okay, and then so I am 99% confident that the true average of maintenance cost per month is between, and it's money, so we'll just say $63.09 rounding up, and $70.91 in rounding. Once again, these numbers do represent things. They represent items and stuff like that, as opposed to the last one that represented percentages. That's why you can kind of do this kind of thing. The margin of error being 3.91 again represents money as well. So this is something to think about. They're not actually percentages. Okay, so for the last one, I'm going to go ahead and throw it in StatCrunch. But a new sneaker claims that it can make male athletes jump higher. A sample of 125 male athletes is asked to jump once with their own sneakers on and once wearing their new sneakers. The average jump increased by 1.5 inches with a standard deviation of 0.5. Find a 95% confidence interval and interpret it. So if I go ahead and jump over to StatCrunch real fast, I'm going to go to T-stats and go to one sample. Again, the T-stat and the Z-stat really are negligible at this point. They should come out to be about the same thing anyway, so T-stat just works just fine. With summary, so we have a sample mean of 120. Nope, that's not right. The mean is 1.5. The standard deviation is 0.5, and the sample size is 125. And I want the confidence interval. I don't want the hypothesis test. So confidence interval of 95%. And I hit compute. And I get my lower limit is 1.4115. And let's see, 1.4115 and 1.5885. Okay. So I'm going to jump back in, because again, even though I did this by StatCrunch, you better believe I still have to write my sentence. So I am 95% confident that the true average jump increase is between 1.4115 and 1.5885 inches. And voila. Okay. So, and again, remember, you always got to write that that sentence regardless of what you do, whether or not you do it by hand or you do it by StatCrunch. Now, for the hypothesis test in this case, it's going to be slightly the same, just a few, well, really it's very the same, just a few simple differences like with symbols and such. We'll go through it with an example again, and like the last time, I'll show you how to do it in StatCrunch on the very last example. So, a report from the Boston News Group states that the mean cost of a speeding ticket includes court fees with $150 in 2002. Local police department claims that the amount has increased. To test their claim, they collect data from a simple random sample of 160 drivers who have been fined for speeding in the last year, and find that they paid a mean of $154 per ticket with a standard deviation of 1754. Is there sufficient evidence to support the police department's claim that fees were greater at the alpha equals 0.01 significance level? Well, for step one, we still have to do our initial evidence phase. The only difference here is that we can't have success failure because there's no percentage. There's no percentage in these. They're only just straight averages. So what we do is we create a new condition that we call nearly normal, which states that as long as the sample size is over 15, it's going to create a normal curve, and as such, it still meets the requirement that we need that was met with the success failure. So, to illustrate this, let's just do step one real fast. So, step one, so we're going to have random. So we had, let's see, 160 drivers were taken at random. 10%. 160 times 10 is equal to 1,600 is less than all drivers in Boston. I do believe that because I've heard that traffic up there is a nightmare. I hear it's worse than in New York. So, and New York's bad. Nearly normal. So this is where the new thing comes in. All we're going to say is 160 is greater than 15. Therefore, it fits a normal curve. It's large enough to fit a normal curve. Okay, and step one is completed. So, step two Step 2 is going to be fairly similar too. The only big difference here is that there's going to be a sign change. Because again, we're not dealing with proportions, we're dealing with straight averages. Therefore, we're going to use mu. So in this case, if we look here, the population parameter is 150. That's what they believe it was. We're trying to refute that. So, step 2. So the null hypothesis would be mu equals 150. And then my alternative hypothesis, the last sentence states there's sufficient evidence to support the police department's claim that fees were greater. So we're going to be greater than 150. And that's it. All we do is we change that symbol. Okay. So now, step number 3, again, is pretty similar to what we had before. The only difference is that we're going to change that standard deviation formula to our new standard deviation formula. So I'm going to have the standard deviation over the square root of n. And so let's see, my standard deviation from the situation was 17.54 divided by the square root of, and there was 160 instances. So 17.54 divided by the square root of 160. So that gives me 1.388, so 1.3867. Okay. So now I'm going to do x minus the mean divided by the standard deviation. And that's going to give me, let's see, from the situation it's 164 if I'm not mistaken. No, 154. 154 minus 150 divided by 1.3867. So 154 minus 150 divided by 1.3867 gives me 2.88. And so if I jump over here to take a look at my z-score chart, 2.88 is 0.998. And since it's greater than, flip back over real fast. Since it's greater than, we're going to do 1 minus 0.998, which gives me 0.002. Now we wanted to weigh it against 0.01, so keep that in mind when we do this last part, because in reality, step 4 is absolutely positively no different. So, step 4 so we had an alpha level of 0.01. We're going to weigh it against 0.01. We got 0.002, which is less than 0.01. So we reject the null hypothesis. We have enough evidence to show that fees are greater than they were claimed. So fees were greater than they were claimed. That doesn't surprise me whatsoever. Okay. So we got 2 more examples. Okay, so second example. A national business magazine reports that the mean age of retirement for women executives is 61.0. A women's rights organization believes that this value does not accurately depict the current trend in retirement. To test this, the group polled a simple random sample of 95 recently retired women executives and found they had a mean age of retirement of 61.5 with a standard deviation of 2.5 years. Is there sufficient evidence to support the organization's belief? So, let's find out. Step 1. Step number 1. So you got random. So 95 women were taken at random. Okay. 2. 10%. 95 times 10 is 950. So, which is less than all women executives. And again, I don't know if that's true. I want to believe it's true, but I don't know if it's true. I'm not going to look it up, so we'll just assume it is. 3. Nearly normal. 95 is greater than 15, so the data is large enough to fit a normal curve. Okay. Step 2. You have the null, which is that the mean age is equal to 61.0. And we have the alternative in that the mean age is just not equal to 61.0 because it just says does not accurately depict the current trend, which doesn't really give us a direction. Let's see. Step 3. So let's see. I need to do 2.5 square root of 95. So that gives me 0.2565. Okay, so I then do 61.5 minus 61.0 divided by 0.2565, and I get, let's see, 1.95, and if I look that up in my chart, it gives me 0.9744. And remember that rule that I said before, and one of my other ones of these. If you're gonna multiply 2 and it's bigger than 1, you have to first subtract it from 1 first. So that gives me 0.0256. And then because it's not equal to, I gotta multiply by 2, which just barely makes it fail, but it does in fact fail. So, step number 4. So 0.0512 is in fact greater than 0.05, just barely, but we fail to reject the null hypothesis. We do not have enough evidence to support the organization's belief. Okay, so this last one I'm going to put it into StatCrunch to find the p-value. So you can see what that's about. The last one states, according to the National Center for Health Statistics, the mean weight for an adult female in the United States is 164.7 pounds. A group promoting healthier eating habits feels strongly that it has made an impact in one community by reducing the mean weight of women in that community. A simple random sample of 39 women in this community yielded a mean weight of 161.9 pounds and a standard deviation of 5.6 pounds. Is there sufficient evidence at any alpha equals 0.01 significance level to say that the mean weight of women in this community is lower than 164.7 pounds? Let's find out. So, step 1. Random. So, 39? Yes. 39 women were taken at random to 10%. 39 times 10 is equal to 390, which is less than all women. I guess we could say less than all women who want to lose weight, but in both regards, I'm pretty certain that's true. Nearly normal. 39 is greater than 15, so it's large enough to form a normal curve. Okay, so step 2, because sometimes I'm feeling like I need to say things in Spanish, which is funny because really the only thing I remember in Spanish is just the numbers anyway. I guess it's kind of ironic since I'm a math teacher. But step number 2, null hypothesis would be that the mean is equal to 164.7, and the alternative is that's less. And let's hope so. I'm always when hear people losing weight. I myself am attempting to lose a little bit of weight myself. Let's hope that happens. I wanted to. Step number 3. So now we're going to go ahead and jump into StatCrunch to see what that has to do, or what we have to do with that. So if I pull that up, go over to StatCrunch, I'm going to go to the same place that I went for my confidence intervals. So tstat, one sample with summary. Now you want to be really careful because you have two means in this case. The sample mean is the one that's going in first. So that's the 161.9. That is not the one from your arguments. Your standard deviation is 5.6. Okay. Your sample size is where's my sample size at here? Oh, 39. And then I am going to go to hypothesis, and this here is where I'm going to put my actual mean for my argument. So 164.7, and I'm going to put down less than, because that was what was my argument. So less than there. I don't need to worry about that confidence interval in this case. I'm just going to compute, and we're going to p-value of 0.0017. Okay. So now the actual situation denoted that it had to be less than 0.01. Technically, it doesn't matter which one because it's less than both of them. So, but since we're talking about this particular situation where it says 0.01, step number 4, 0.0017 is less than 0.01. So we reject the null hypothesis. We do have enough evidence to show the mean weight in women is lower. I always just realized I kind of refer to myself in the royal we. Maybe that says something about myself, that I think I'm royal. At any rate, that's pretty much it for this. I will see you in the next video. Unless, of course, this one didn't take. In which case, I'll see you in this video one more time.